Okay, let's talk about excited states of helium. So this is an interesting case where uh, exchange symmetry gets more interesting. Um, let's consider initially the ground state of helium. We have two electrons in a 1s uh, orbital like so. Now we can imagine there's of course this empty 2s orbital. And we can imagine bringing in a photon, right, to promote one of the electrons from 1s to 2s, like so. Um, and you can imagine, of course, there would be other possible configurations that we might want to consider, such as this is the case here where the spins are anti-parallel. We could also imagine a case where we have an excited state that looks like this, where both of the spins are pointing the same direction or parallel spins. And so these are essentially the two basic cases that we'll want to look at for excited helium. And there's this issue, there's the case where the spins are anti-parallel, and there's the case where the spins are parallel. But some questions arise. Are both of these pictures essentially valid? And how do we make sure that our wave function description is consistent with the Pauli exclusion principle? And is it perhaps the case that one of these configurations does not um, that does not agree with the Pauli exclusion principle or somehow violates it? And then finally, there's the question of if there are multiple different excited electronic configurations, which are the lowest energy? And then there are some other considerations such as degeneracy. So summarizing, which are the proper configurations? How to express the wave function, and um, energy levels, or what are the relative energies of these different configurations. And so we'll address these questions. First, let's look at uh, a proposed wave function for the anti-parallel case, which corresponds to this type of drawing over here, where we have sort of the spins are paired, but they're in different energy levels. Okay, so it turns out that the wave function for this helium excited state can be written as follows. So that's psi for helium excited. there's some sort of normalization constant. We represent these wave functions like we did previously. Oh, excuse me, I need to plug in my laptop. Okay. We use these representations here to represent the 1s and 2s wave functions of the helium atom, and so that's a shorthand that we ran into before. So this is essentially the spatial part of the wave function. And sorry, oh, this is, okay, alpha 1, alpha 2. Sorry, this is the, not here. Bear with me. This is this kind of configuration where they're parallel spins. So both spin up. And so the spin part of the wave function containing the alphas is symmetric with respect to exchange of the spin labels, whereas the spatial part, these orbitals in the curly braces here, that part of the wave function is anti-symmetric with respect to exchange of the spin labels. In other words, if we swap the labels, right, if we apply that exchange operator that we talked about, then it will change the sign of the wave function. So overall, when we change all of these labels for the product of the spatial part and the spin part of the wave function, we get a net wave function that's anti-symmetric with respect to exchange of the electron spin labels. So this appears to be, so it's anti-symmetric with respect to exchange. In other words, 1 goes to 2, etc. And so therefore this is consistent with Pauli exclusion principle. The quantum mechanical version. There's also an essentially identical state where they're both spin down, right? And so it's going to look essentially just like our previous state. Oops. Both spin down. Okay, and it's going to look essentially just like our previous state, right? So the spatial part looks the same, except that we've replaced the alphas here with betas. Okay, so that's the both spin down state. And it turns out that there's another state that looks a little bit like this, that doesn't have a corresponding neat kind of picture in terms of the arrows. So here's a third state which shares a lot of properties, and it turns out is degenerate with this degenerate with these two states that I talked about already, and it looks a little bit like this. It's kind of long. Psi for helium, excited. This is the third one, and it has a normalization constant, 1 over 2, and then it has two kinds of linear combinations. There's this, there's of course the 1s, 1, 2s, 2, minus 1s, 2, 2s, 1. Then there's also this other state, this other part, the spin part looks like this, where you have alpha 1, beta 2, plus alpha 2, beta 1, and curly brackets. Those last two are supposed to be multiplied together. Sort of ran out of space. Bear with me. Okay, so it turns out that these three states or electronic configurations all have the same energy unless there's a magnetic field. So they are split by a magnetic field. There's a sort of Zeeman splitting of the excited state helium. The ground state of helium is not split by a magnetic field, according to the typical Zeeman picture. So these there end up being three states with this kind of spatially antisymmetric wave function. The spin part is symmetric, and they have the same energy. So there's three degenerate states, and they are called a triplet. There's a second case. There's another valid configuration that has a different energy level, and that is this sort of spin paired-ish type configuration where we've got one electron in 1s and another electron in 2s. This is sort of again, these diagrams, they're a useful starting point, but they don't give the whole picture. Nevertheless, based on this picture, we can construct another wave function where the spins are sort of flipped. But of course, this picture, this literal picture, would violate the Pauli exclusion principle because it's saying that the 1s electron is spin up and the 2s electron is spin down, and that would, in effect, be distinguishing between these two electrons. And so we need to use a linear combination to make a proper wave function that doesn't distinguish between electrons. Okay, so let's do that. The singlet, this is called the singlet state. And it looks like this. Psi equals 1/2, 1s 1, 2s 2, plus 1s 2, 2s 1, and this one, the spin part looks like alpha 1, beta 2, minus alpha 2, beta 1. So this looks rather different than the other wave functions in that the spatial part here is symmetric with respect to exchange. And the spin part is antisymmetric. With respect to exchange of electron labels. Now it turns out there's only one way to represent this wave function in a way that doesn't violate the Pauli exclusion principle. And in fact, there is only one state like this. And so this is called a singlet state, representing 1. This state is not affected by a magnetic field. It has no sort of net spin. And then that raises the question, okay, so now that we've looked at these states, we've identified these sort of two kinds of helium-excited states. Do they both exist? And the answer to that is yes, they do both exist. And then another relevant question is, which is the higher energy state or set of states, and which is the lower energy state? In other words, which is the lowest energy excited state, and which one is a little bit above that? And it turns out that the triplet state is lower in energy. And there's a couple of reasons, a couple of ways to try to think about that. One way to think about that is that we know that there are Hund's rules, or the Busseit rule, which state that the lowest energy configuration, all else equal, is the configuration that has highest spin multiplicity. In other words, the one that has the most unpaired spins. That's also the Busseit rule. Like, for instance, if we have two degenerate, let's say we have two degenerate levels, and say these are, well, let's say 3, and we'll start putting electrons into say 3 of the 2p orbitals. The first one we put in is going to go here. The second one that we put in is going to go there, and the third one is going to go there. And that's the lowest energy configuration for 3 electrons in the 3 2p orbitals. We could try to pair them up, but that would be a higher energy configuration. Right? So this would be the lower energy configuration. So this is consistent with that, saying that if we have unpaired spins, we have all else equal, we're going to have a lower energy configuration. As long as we don't do anything that violates Pauli's exclusion principle, like putting 2 up spin electrons in the same orbital, right? That would violate Pauli exclusion principle. Okay, so that's one way to look at it. Another way to look at it is that essentially the fact, if we look at these wave functions, let's look at this one again. Let's look at maybe, one of the simpler ones, this one up here. The spatial part is antisymmetric with respect to exchange, meaning that this first set of terms, this 1s1 times 2s2, has opposite sign of the next term, which is 1s2, 2s1, meaning that it's like those wave functions are out of phase. So if we think about the electrons sort of orbiting around the atom, this corresponds to them sort of staying on opposite sides. Again, this isn't literally true, but there's some truth to it, thinking about the electrons tend to avoid each other when they're in this spatially antisymmetric state. And since they are avoiding each other, or they're staying sort of on opposite sides of the helium nucleus, then that means that there's going to be less electron-electron repulsion. So the electrons avoid one another. due to this kind of Pauli exclusion, or due to the spatial parts being kind of out of phase with one another. Or staying on opposite sides of the nucleus, and therefore we have reduced electron-electron repulsion. And therefore lower energy. So it turns out that the triplet state is lower in energy than the singlet state. And this may seem somewhat counterintuitive if you're used to thinking of electron spins as little bar magnets. And you know that if you put two bar magnets together, then the lower energy configuration is sort of if you have north and a south, and then I stick another one next to it, right? This would be the lowest energy configuration. Opposite poles attract on our magnets. But this kind of analogy breaks down in the case of electrons, and it's because of this sort of strange quantum mechanical interaction, the fact that electrons that have the like spin tend to avoid each other, and this is a statistical tendency. It has to do with some very deep physics having to do with the symmetry of relativistic spacetime as it applies to the interactions of particles. And so the electrons tend to avoid each other when they have the same spin, and this reduces electron-electron repulsion and lowers the overall energy of the molecule. Something similar happens also with molecular oxygen. The ground state of oxygen is actually a triplet state, and that has unpaired spins. And singlet oxygen exists. You can prepare it by essentially exciting with a near-infrared photon or by using a photosensitizer dye. Singlet oxygen is a higher energy form of oxygen. It has a fairly short lifetime. It has a short lifetime because it's very reactive. In fact, singlet oxygen is a well-known reactive oxygen species. It's probably what's responsible for things like sunburns, or it's involved in sunburns due to the interaction of light, UV light, with your skin, and then molecules in your skin donating energy to oxygen to make singlet oxygen, which is very reactive and then causes cellular damage. All right, so that's part of the helium picture. Another way to look at helium is to consider something called a Jablonski diagram, or fluorescence and phosphorescence of helium. So we can consider sort of grouping these various excited states and ground states together in a diagram called a Jablonski diagram. Where we have something that we'll call an S0 state. That corresponds to, so that's an S0 state of the molecule. which is a shorthand for an electronic configuration that looks like this. Then we have our singlet excited state. We'll call that S1. That corresponds to anti-parallel spins. Then over here we have our triplet state. There are 3 states. We'll just use one line because we'll call this T1. And that will help us keep track of the fact that there are 3 states like that. So if we have a molecule initially in the ground state, we can bring in a photon, promote the molecule to the excited state, to this S1 state. In other words, we're moving one of the electrons to the from 1s to 2s. And it turns out that photons don't carry the right kind of spin to flip the spin of an electron. So this is actually how the process goes, that you have to go from an S0 state to an S1 state. You can go directly to a T1 state, but that's a much lower probability process. Most of the time, if a helium atom absorbs a photon, it's going to go into the S1 state. However, so then it's going to stay around in that S1 state for a while. It can relax back down to S0 and re-emit a photon. And that's called fluorescence. Or it can maybe collide with another helium atom, pick up enough angular momentum in the process to go from the S1 to the T1 state. Once it's in the T1 state, there's no easy way for it to go back to the ground state because it requires flipping a spin, and there's just nothing around to give it that angular momentum needed to flip that spin to go back down to S0. So this is a long-lived state, and it decays, sorry, I'm going to cross the lines there, it decays by phosphorescence. And this process, this other arrow here, is fluorescence. So this is a phenomenon that is widely seen. Helium is, of course, the simplest case where we see this sort of singlet, triplet, fluorescence and phosphorescence type phenomena occurring. But of course, there are many fluorescent dyes, there are many inorganic pigments or molecules that, or solids that also display this kind of phenomenon. And the triplet state can be very long-lived. In fact, in phosphorescent pigments, like those little star stickers that parents like to put on kids' ceilings, that sort of thing, those have a phosphorescent phosphor in them that has a very long-lived triplet state that continues to emit green photons very slowly from this sort of forbidden T1 to S0 type transition, and it emits those that it stays in that T1 excited state for several minutes with a slowly decaying population, rate constant of on the order of one per minute, something like that, and then it slowly emits a green photon, say in the case of those stickers. All right, so that's, I guess, all I have to say about helium at this point. And next we will move on to Hartree-Fock self-consistent field theory, and I will see you next time.